Okay, so quantum architecture. Basically, the way that a quantum computer works is it's made up of these things called qubits. Qubits are subatomic particles that are embedded in silicon crystals, right? So basically, these qubits are placed inside a really strong, really cold, or placed inside of a really strong magnet and like cooled to really low temperatures. Now it's cooled to really low temperatures in order to prevent or keep the qubit stable. So when a qubit is at room temperature, it's not really, like, you can't really measure it that well. And then as far as why it's in a magnet, or a really strong magnet, that would have to do with the fact that it allows one to differentiate when the qubit is in a spin up or a spin down state. So, a qubit is basically different from a C bit, and that a C bit or classical bit can either be 0 or 1, right? But a qubit can be both at the same time. So this kind of both state is what's known as superposition, which I'll discuss in the next slide. And then to describe what 1 and 0 means for a qubit, the one state for a qubit is basically known as spin up. So that's when the particle is oriented in the up direction, and then the 0 state is basically known as the downspin, so it's oriented down. And then superposition. So superposition can be thought of as a vector of probabilities. The probability of a particle being in a spin-up position is determined by taking the squared magnitude of the first component of the vector. And then the same applies for the second component. So the second component would be the probability that it's in a downspin state. So the one constraint that applies to qubits, right, is that the sum of the magnitude squared of both components must be equal to 1. So basically that it's the reason why it's 1 is because if you were to be over 1, then you would have a probability greater than 100% of it being in either a upspin state or a downspin state, which really doesn't make a lot of sense if you think about it. Entanglement is another thing that quantum computers use. The entanglement is basically when you have 2 qubits, right? And basically the spin of one qubit when it's observed determines the outcome of the other qubit when it's observed or measured. And that's used in a number of different algorithms as well. Teleportation. So the problem that teleportation basically solved, and why it's used in quantum computers and how it makes them work, is basically that when you need to copy data, you can't really copy data using a quantum computer because measuring the spin of a qubit basically destroys the data being transferred. So what you have to do is instead you have to teleport the data from one qubit to another. Otherwise, you can't really transfer data between qubits. And that concludes my presentation. So now onto my project. So for my project, I decided to convert quantum computing gates into classical computing gates. There's not really a whole lot of like applications for like why you would do this, or like there's not really a great reason for why you would want to do something like that, but it still serves as like a cool way to kind of understand how quantum gates work, and like, you know, just to do problem solving with them. So for the first one, the way that I converted, or I made a classical gate, was that I basically represented bits as whenever there's a 1, right, that I'm inputting, turn it to, or flip the qubit, right, in the 0th position, right, and then flip it again because it's not, right, and if it's not 1, then it would just skip over this part and it would go straight to here, which would make it 1, and then measure the outcome of what it is, or the measure the qubit, right, and then send it off to some quantum computer in London. And then, so I've pre-ran all of these gates because it takes a while for them to run. But I'll run like 1 or 2 of them just to demonstrate to you that they all work. You know. So while this one is running, I'm going to explain the reasoning and logic behind the XOR gate. So I did the same representation for bits in the XOR gate. Oh yeah, and this is the result. So I did the same representation, and then the way I was able to basically kind of simulate an XOR gate on a quantum computer was that I used the control not gate. So the interesting thing about the control not gate is it basically it has a control bit and a target bit, right? So when the control bit is 1, then the target bit is flipped. So the nice thing about that is that it kind of results in an XOR gate, but I can further explain specifically why that is. So basically, say if the in the instance of this one, right? I left something out. Also, I forgot to mention. I'm not just saying the controlled NOT of this circuit to get XOR. I only measure the second bit, right? Because the second bit is ultimately the one that's the target bit that's being modified. Anyway, back to the explanation. So when the first bit is 1, right? Say in this example, then this would be flipped to 1. So 1 0 XOR is 1, and then if it's 1 1, right, it flips the target bit again and it becomes 0. And then I didn't really put the ones where it starts with 0 because in both cases 0 0 and 0 1, 0 0 would be 0 because the control bit is 0, and then 0 1 it would be 1 because the target stays the same. So because the control bit's 0. And then if I run this, that'll run, and I'll now explain AND. So AND, I basically it got a little bit more complicated because I had to use this gate called the Toffoli gate, which is this one right here. And the way that the Toffoli gate basically works is you have 2 control bits and then 1 target bit. So the way that I basically simulated it in AND was that I had 2 control bits, which is the 2 inputs that I take in, and then default 0 target bit, right? So when it starts, it basically looks something like this. So, oh yeah, and this is the result of the previous one. XOR 1 0 is 1. When it starts, you kind of get something like, we'll say the input is 1 1, like I did down there, and then it starts out like that, right? And then basically, since the control bit, it has 2 control bits, or I mean, since the Toffoli gate has 2 control bits, it looks to see if they're both 1, and if they're both 1, it switches the target bit to being 1, which is, I mean, that's an AND gate. So that's why it works, basically, is just because both control bits have to be 1 in order for the target bit to flip. And the target bit is by default 0, so it only ever flips to 1 when both control bits are 1. And then I'll run this one as well. Okay, so the NAND gate was pretty simple. I just knotted the output of the AND gate not really a whole lot that needs to be explained there. And then the OR gate was slightly a bit more complicated. I basically said, on seeing a 0, flip the bit, right? So the representation is slightly different from how I was doing it previously. Basically, in the past, what I would do is I would say, if there's a 1, flip the bit. However, with the OR gate, I'm saying if there's just a 0, flip the bit. And the reason for this is basically because the circuit to convert an OR to a AND bit is basically you not 2 inputs of the AND gate and then you not the output. So that's basically what I did. I mean, basically the Toffoli gate is equivalent to, in the way that I set it up, equivalent to an AND gate, because it's 2 control bits and then a default 0 output bit, right? And then I out that NAND, or that AND gate with 2 knotted inputs, and I measure the output gate. So as you can see, 1 1 is that. If you put like 1 0, it would also be true. So I'll run that as well. And then I decided, just for kind of fun, if I could kind of extend these gates to something that like we kind of learned in class. So I decided to do a half adder. So half adders, it's pretty simple. You just do an XOR gate and an AND gate, and the XOR gate is the sum, and the AND gate is the carry. I wanted to do or go a little bit more complicated, but there were some issues that arose with the fact that like if you stack or the way that the controlled NOT gate works, it kind of modifies the value of that qubit basically. So you'd have to kind of figure out a way to order the controlled NOT gates, and I really just couldn't figure that out. So, but I was able to get the half adder working, and so the half adder, basically the second bit would be the carry, and the first bit would be the sum. So in this case, 1 1 would be 1 0, because it's 1 carry and then 0. And that was the highest probability. I mean, if I ran it again with 1 0, it would be just 1, because 1 plus 0 is 1. So yeah, that is my project. And I really enjoyed it, I like the fact that you were able to, or that I was able to send information to a quantum computer across the world, very interesting stuff. So